Well, this is the beginning of chapter 4. We're going to talk about moments today. And whenever you have a force applied to a body, it may have a tendency to twist or to rotate or to bend. And our textbook definition or little note here suggests that when a force is applied to a body, it will produce a tendency for the body to rotate about a point that is not on the line of action of the force. So let's look at this picture. We have a bar that's attached to the wall, and we have a force that is applied, 100 Newton force out there at a little bit of a distance. The line of action is any place along where the force might be projected to be, either before the force is applied or after the force is applied. Any place along that line is called the line of action. The point about which it may tend to rotate would probably be where the wall is, where it's attached to the wall. You can see that when you push on this thing, it's going to have some tendency to rotate like that, and that's called the torque or the moment. You may remember from physics, talked about simple machines and levers and mechanical advantage. And if you had a rock that you were trying to lift up with a bar, you might want to try a force here. And if you had a fulcrum or a point of rotation right there, you could see that the bar or the rock would have a moment about that point of rotation, which would be the weight times that distance. And the force that you're looking for would have some force times its perpendicular distance. In other words, we don't want to look at that distance, we want to look at the perpendicular distance or the cosine of that angle. So the magnitude of the moment then is defined as the magnitude of the force times the magnitude of the perpendicular distance away from that point of rotation. You can see here that in this picture that there are equivalent moments. If you had 100 newtons times a bigger distance, that would be the same effect. It's going to have a moment about that point. It'll have the same effect as a bigger force times a smaller distance. The directions of moments are important, and in two-dimensional work we will define, this is convention, that will define counterclockwise as positive. So counterclockwise is positive, clockwise would be negative. We'll talk a little bit more about that as we go. Alright, let's look at this example from our textbook, and you can see that here's several of them where we're trying to find the moment about the point of rotation, or in this case about point O. Most of the time the point of rotation that we care about, at least at the beginning here, will be given to you, and as we get a little more advanced, then you may choose what the point of rotation or where it's logical to take a moment or to find the moment. Alright, so we're here. Let's find out the moment about point O of this force. That's 100 newtons times 2. That looks like it's going to be 200 newtons around that point. That's easy to see because it's easy to see the perpendicular distance. If you can't see the perpendicular distance directly, you have to kind of use a little logic and use the line of action. For example, this one right here has a 50 newton of force applied way out here. The line of action is found by kind of doing this dotted line business out to there. What you're really looking for is that perpendicular distance there. The line of action times the perpendicular distance. Perpendicular distance to the force. And it's pretty easy to see that this distance here is going to be the same as that distance there. We are finding a clockwise moment, so that's a negative moment. Same thing with number C here. If you're applying the force out here, we're looking for that total distance right there to give that moment. You can see by the shadow here, the little shadow here where it's the direction that it's trying to bend or trying to rotate. And that may be a helpful way of understanding the directions of the moments, is which way would it bend if it was a real configuration that you're trying to understand. For example, this one right here, number D, we have a force applied right out here, and we're looking for the moment. Well, does the moment have something to do with this distance, or this distance, or this distance? And the answer is no, because the force is right here, and the only line of action is right there. So we're really looking for that distance, which is going to be the same as that one. And you can see how it's calculated. Same thing over here. And number E here, the force is applied here, and the perpendicular distance is that right there. In both of these cases, we're trying to rotate it in this direction, so those would be positive moments as we look at that. Now moments are going to be positive or negative based on the direction of the moment, clockwise or counterclockwise, not on the direction, or not based on the direction of the forces necessarily. For example, look up here. We have this negative moment. In other words, it's going in the negative y direction or the negative j direction. It's causing a bend going this way, and it's going to cause a negative moment, meaning it's a clockwise tendency. Same thing here. I have a positive force. It's trying to rotate it going up like this way, and that'll become a positive moment, which is counterclockwise. Over here on the right, though, we have a negative moment, which is causing a counterclockwise rotation. So I'd have a negative force causing a positive moment. Or in this case, I have a positive force causing a negative moment. So it depends on not the direction of the forces, but the direction of the moment. So it's pretty careful, the direction of the twist or the rotation. And resultant forces or resultant moments are very important. We will often have multiple forces applied to a body, and we want to find out the total moment. And you can see by this example how you add them up and find out what the total moment about point O is. Now, very often the point of rotation is a natural point of rotation or a tipping point. For example, we already talked about a force trying to lift up a rock. It could be a teeter-totter or some sort of something where it's pretty obvious that will be the fulcrum or the point of rotation. If you're trying to tip a table over, it would make sense that it would rotate about this point over here, not about this point as it rotates. Same thing if you had a sign or something vertical. If you're pushing here, it may tend to rotate about that point. If you had a wheelbarrow and you're lifting it up, say you have something pulling it up right there, the point of rotation may be the center of the axis. And we'll again either specify that point of rotation for you, or you can choose the point of rotation depending on the type of problem that we're looking at. All right, a couple of principles I want to go through. The first one is called the line of action, or what is the line of action. This is called the principle of transmissibility. So if you have an object here and you're applying a force here, that is going to have the same effect as if you applied the force here. In other words, we talked about in chapter 2, there is no difference between pushing and pulling, and that was the beginning of our understanding of the principle of transmissibility. So the line of action of this force means that the force can be applied at any point along that action, and it'll have the same effect. No difference between pushing or pulling. And the other principle we'll call is principle of moments. And another name for that is called the Varignon theorem, or Varignon's theorem. And what it says here is that if there is a force applied at an angle, we're only interested in the component of that force that causes an effect. So what we can do is we can sum, or we can break that force up into its two components, and then add the moments caused by those components separately. So for example, we have a force here at some angle. There would be a sine component here and a cosine component like this, and we add them together. In other words, some of the moments about point O is going to be equal to the sine component times this distance plus the cosine component times its lever arm. Now, as it turns out, when the lever arm is 0, in other words, this component here is going all the way through the line of action of that, or the line of action of this component is going through the point of rotation, so the lever arm will be 0 in this case. If we put some distances in there and some values of the force and the angle, then you can see that the magnitude of the moment can be calculated easily. Well, let's take a simple example here and find out the magnitude of the moment about point A of these three forces. First of all, let's use Varignon and break up the forces at the angles and come up with their components. So in other words, there's going to be a component going in this direction and a component in this direction from that guy, and then that will be the 4/5 component of 500. This one will be the 3/5 component of 500. F3 over here has a component in this direction. That will be the cosine component, so that'll be 160 cos 30, and then this one will be the sine component, so it'll be 160 sine 30. Alright, now to find out the total moment about O, we just add them all together. So let's just do that. Sum of the moments about point O. Now I didn't talk about this before, but let's refer to this just a little bit. We should always put a positive direction when we're summing our, or when we're doing our moment calculation. Let me go back real quickly to the textbook, and you can see how they did it in here. So I should have pointed this out before, but if you look carefully at this, they use this little designation here where they are going positive. So that says that counterclockwise is positive. In general, we will always use counterclockwise as positive. I don't think there's very many examples where we will do anything different. So you can either put your little positive sign on the left hand side like that, or you can put it above the moment like I tend to do. So I'm going to say sum of the moments about point O is equal to, let's just add them up. First of all, we have this 375 times this lever arm. Well, that's pretty easy to see. And that's going to be in the negative direction. So that's negative 375 times 8. Now let's look at each of the components in red here. So I'll also have this 4/5 500 times its lever arm of 14. The 3/5 times 500 actually has 0 lever arm. In other words, it is the tendency to, or the, sorry, it keeps, the lever arm here is 0 because the line of action of this component goes right through point A. So I'll say that I'll go ahead and put it in here, and you can see that it'll have a 0 lever arm. So when you do your work, you can leave them out if you can see it's pretty obvious that it has a 0 lever arm, but I'll put it in here for right now. So I'll say that that's plus 3/5 times 500, and the lever arm is 0. Alright, let's look at the other two components. I also have this 160 down here, so I'll say that that is negative 160, and the magnitude is cos 30. The lever arm is going to be the 14 plus 5, so that's 19. Then the last component we want to consider is this 160. Now this 160 has this lever arm right here, 0.5, and it's actually tending to rotate it like that. So that will be a positive component. So let's go ahead and put that there as positive 160 sine 30, and its lever arm is this little piece right there, 0.5. And then when you add all those together, you'll get negative 11,190 pound-feet. And that's the answer we're looking for. Alright, well this one here, 4-10, has a tendency to rotate about point A. We got two forces pushing up on this bar and has a tendency to rotate about point A, so that's what we're looking for. And we can do this in a number of ways, but what we're looking for are the perpendicular distances of the components of the force. So let's break the forces up into their components. So I'll say that there has a FB, and it says that FB is equal to 30 pounds, so it'll be 30, and this will be the cos of 25 degrees. And then there's a component going in this direction. That'll be 30 sine 25, sine 25, sine of 25 going in that direction. FC has a magnitude of 45, so there'll be a component this way, so that'll be 45 times the cos of 30, and then a component going in this direction, 45 sine of 30. Alright, when you do all that, you can see that these are the two components that have perpendicular lever arms. These two go through the line of action of the force, or go through the line of, the line of action of these two components goes through the point of rotation, point A, so we actually don't even have to consider them. So let's sum the moments about point A. And I'm going to do positive, go that way. So all I have is this 30 cos 25, and it has a distance of 2.5. And then I have 45 cos 30, and its distance is 2.5 plus the 0.75, so that would be 3.25. And the total there is going to be 195 pound-feet. Okay, so I think you can kind of see that it's only the perpendicular distance that counts. It can be rotated up in the air like that, and that is no problem. Well, here are a couple of problems that I'd like you to pause the video and work on just a little bit. That's what we would do if we had a face-to-face class here. So what I'm looking for, or what I'd like you to look for, is the moment about point O of these two forces and the moment about point O for this force. And if you could work on those things and then start the video once you've solved these. Alright, here are the solutions. For the first one, the moment about point O. Again, put the positive counterclockwise direction. We have this 240 times this total distance going in the negative direction, so that's probably pretty easy. Then this one has two components, 4/5 going this way and 3/5 going this way. It's only the 4/5 component that has a lever arm. The 3/5 component goes through the line, or the line of action of the 3/5 component goes through the point of rotation, and so you can see that the total moment is going to be equal to 0. In this second one, we have a moment caused by this force, and this is the perpendicular distance here. So the only problem here is trying to find out what the perpendicular distance might be. And so what we're going to look for is that it's going to be 600, and the distance, if you look, is going to be 4 feet plus the cosine component of 45 minus the 1 foot. And that's the way I did this, is the total distance will be 4 plus 3 cosine minus 1, and that'll give us a moment about point O is counterclockwise positive. Now I've got another calculation here using R cross F, and we'll talk about that a little bit later, but for right now we're just going to consider that it's 3,072 pound-feet.